Hi everybody, this is the first video of our course, and today we will be talking about some of the historical context and motivation of quantum mechanics. I'd like to start off with kind of an oversimplification, just to set the scene of where science stood in the late 1800s, which is really where we begin our story. In the late 1800s, scientists saw matter, the objects around us, as consisting of particles, and light as consisting of waves, and those two things being completely different from each other. And all of the observations that had been made about chemistry to be more or less unexplainable. I will elaborate a little bit on what I mean by that. When I say that matter consisted of particles, I mean that Newton's laws of motion, which dated back to the late 1600s, were more or less still thought to be correct. Newton's laws had been extended by Lagrange and by Hamilton to deal with more complicated systems, but still the basic laws were still thought to govern the motion of everything. Meanwhile, light was seen as being completely different. Light consisted of waves, and that had been theorized and demonstrated by the late 1800s, and light was really seen as being completely different from matter. Meanwhile, scientists were beginning to make some observations about chemistry. The patterns that form the basis of the periodic table were being observed, and Mendeleev was sort of cataloging these in the earliest forms of the periodic table, but the basic physical reasons for those patterns were not well understood. Before we move forward, I'd like to review a few basic concepts related to light waves. The reason it was believed that light consisted of waves was largely because light forms interference patterns. In other words, light waves add and subtract from each other to make bright spots and dark spots, in the same way that water waves add and subtract to make particularly high locations and low locations, like the picture on the right. And when we talk about waves, we first of all can talk about their wavelength, the length from one peak to the next peak, and also their frequency, the number of cycles that pass a given point in a given amount of time. For light waves, the important equation that we want to have in mind is c equals lambda nu. C is equal to the speed of light, and at least to a good approximation, in vacuum, c is constant. C is equal to 3 times 10 to the 8 meters per second. And that constant for all light is going to be equal to lambda, which is the wavelength, times nu, which is the frequency. We can see from this equation that wavelength and frequency are inversely proportional to each other. In other words, as the wavelength gets longer, the frequency gets lower. We can see that inverse relationship in this animation. This animation is showing two waves that are moving at the same speed, so they're moving left to right at the same speed, and we have a blue wave that has a shorter wavelength, and an orange wave that has a longer wavelength. And actually, it's a factor of 2. The orange wavelength is twice as long as the blue wavelength. And as a result, if you look at the frequency, if you focus on a particular point and look at how many cycles of each wave passes that point in a given amount of time, you can see that the frequency of the blue wave is twice as large as the frequency of the orange wave. So this follows this relationship that we expected. We know that the speed of the waves are all the same as each other, so the shorter the wavelength, the higher the frequency, and vice versa. The two things are inversely proportional to each other. When I talk about light, I'm actually talking about light more broadly. Visible light, the colors that we see, is actually just a small sliver of the electromagnetic spectrum. So when we're talking about light, waves that travel at c, the speed of light, we're actually talking about all electromagnetic radiation. Ultraviolet, X-rays, infrared, microwaves, in addition to visible light. Just to make sure we're all on board, I want to ask a couple of quick questions. I will pause for a few seconds after each question, but if you'd like more time to think about it, I would encourage you to hit pause and think about it for as long as you'd like. The first question is, which has a higher frequency, blue light or red light? Hopefully you decided that blue light has a higher frequency. You can see from the picture on the bottom that red light has a longer wavelength. The red end of the spectrum is associated with longer wavelengths than the blue end of the spectrum. And because wavelength and frequency are inversely proportional to each other, blue light, which has the shorter wavelength, is going to have the higher frequency. Second question is, which travels at a faster speed, blue light or red light? Hopefully you didn't get tricked. Blue light and red light travel at the same speed. I know this sounds obvious, but blue light and red light both travel at the speed of light, which is a constant. Okay, so now that we've established where things stood in the late 1800s, we can start to move forward and think about the origins of quantum mechanics. While it's fair to think of matter in isolation as consisting of particles and light in isolation as consisting of waves, it turns out that when the two interact with each other, some unexpected things happen. And for the rest of this video and the next video, we're going to be talking about a few of these famous observations that led to the insights that were the origins of quantum mechanics. The first one is something called Blackbody radiation, which was explained by Max Planck in 1900. The second is the photoelectric effect, which was explained by Albert Einstein in 1905. And the third, which will come in the next video, is the idea that every element has a characteristic emission spectrum, which was explained by Niels Bohr in 1913. So these are all very famous physicists, and I think it's telling that all three of them, Planck, Einstein, and Bohr, won Nobel Prizes in physics for this particular work. We'll start with blackbody radiation, which was the first sign that something wasn't quite right with classical physics. In physics, a blackbody is an object that absorbs and emits all colors in the spectrum. This sounds like kind of an abstract concept, but to a good approximation, planets and stars actually behave as blackbodies. It turns out that classical physics predicts that a blackbody should radiate more and more intensity as the frequency of light increases. In other words, at high intensities, classical physics predicts that a blackbody would radiate an infinite amount of energy. So this statement shouldn't be obvious to you. We really aren't going into the physics required to understand why classical physics would predict this. But this statement that a blackbody should radiate an infinite amount of energy at high frequencies should set off alarm bells in your head. This idea that an object could radiate an infinite amount of energy doesn't seem possible. And this classical prediction is actually called the ultraviolet catastrophe. Just to be clear, the ultraviolet catastrophe does not actually happen. The ultraviolet catastrophe is the classical prediction of what would happen if classical physics were correct. But we know that an object doesn't radiate an infinite amount of energy at high frequencies. For example, if you look at stars, they shine at different colors depending on their temperature. So we know that real blackbodies actually have a peak radiation that depends on their temperature. This apparent problem with classical physics was first rationalized by Max Planck in 1900, who first proposed this pretty amazing idea that energy is quantized. What Planck said was that a blackbody absorbs and emits radiation not as continuous waves, but actually as little packets of energy that come in specific values. Planck referred to the packets of energy as quanta. You'll hear this word a lot. The singular is quantum, the plural is quanta. And Planck said that these energies were proportional to the frequency of the light. So this equation at the bottom of the slide says E equals NH nu. E is the energy that a blackbody is absorbing or emitting. N is any positive integer, 1, 2, 3, 4, 5. Nu is the frequency of the light. And H is a constant. It's now called Planck's constant. Presumably Planck himself didn't call it Planck's constant. So this equation is telling us that the energy that can be absorbed or emitted by a blackbody is proportional to the frequency. So it's some constant times the frequency. The reason why this helps to explain that the ultraviolet catastrophe doesn't actually happen is that you can imagine that as you get to higher and higher frequencies, where you might have expected infinite amounts of energy to be emitted, these quantized energy levels get farther and farther apart. So there are fewer and fewer possibilities for light to be emitted at high frequencies. I want to emphasize how strange this should seem. This idea that energy can only be absorbed and emitted in particular quantized amounts. This is kind of like saying that a car can only travel at specific speeds. This quantization of energy is really not something that we see in our everyday experience, but it's something that we only notice for very small things and for very small amounts of energy. If you look at Planck's constant h, it's a really, really small number. So while this energy is coming in little packets, they're really, really tiny packets that it's hard for us to notice unless we're looking at things at the atomic level. So we've arrived at this idea that the energy levels in black bodies are quantized, which intuitively feels very strange. And we're going to push these ideas even farther when we talk about the photoelectric effect. The photoelectric effect is the experimental observation that when you shine light of various frequencies at the surface of a metal, only certain frequencies, only high frequencies above a certain threshold, cause electrons to be ejected from the metal surface. So, in other words, as this picture illustrates, if you shine red light at the surface of a metal, in this particular example, nothing happens. Red light does not eject electrons from the metal, no matter how bright that red light is. As long as it's red, it doesn't eject electrons. Green light, which as we know has a higher frequency, does eject electrons. And blue light ejects electrons and causes those electrons to fly off the surface of the metal even faster. If we show this in graphical form, it looks something like this. In the graph on the left, we see that if we shine light at a low frequency, a small value of nu, nothing happens. No electrons are ejected. But once we hit a certain threshold frequency, everything above that does cause electrons to be ejected. And in the graph on the right, we see that above that threshold, the electrons are ejected faster and faster. Specifically, it's the kinetic energy of the electrons that's being plotted, and kinetic energy is proportional to velocity squared. So, as we get to higher and higher frequencies above that threshold, the electrons are being ejected at higher and higher kinetic energies, or higher and higher speeds. It turns out that this is another phenomenon that goes against what would have been expected in classical physics. If light actually behaved as waves, as it was believed in the late 1800s, then a high enough intensity of light, regardless of the frequency, should be enough to cause electrons to be ejected. In other words, if we shine red light at a surface and no electrons are ejected, you would expect, based on classical physics, that if we just shine more red light, more intense red light that had more total energy, it would cause electrons to be ejected. But as we've seen in the photoelectric effect, that's actually not what happens. No matter how bright the red light is, nothing happens. No electrons are ejected. So, we need a fundamentally new idea to explain this, and it was Albert Einstein who came up with that idea. Einstein's idea was that what the photoelectric effect is telling us is that light is not really behaving as waves in this case, it's really behaving as a beam of particles, and those particles are now called photons, where the energy of each of those photons is proportional to the frequency of the light. In other words, you can picture the photoelectric effect as basically throwing a bunch of objects at the surface of the metal, such that every one of those objects, say they're baseballs or something like that, every one of those baseballs is knocking an electron off the surface of the metal and causing it to fly away. So the question becomes, does each one of those objects, does each one of those photons have enough energy to knock an electron off the surface of the metal? If it does, then it transfers its energy to the electron, causes the electron to fly away, and the more energy the photon has, the faster that electron is going to fly away. The more of its energy is going to be converted to kinetic energy of the electron. So just to see if we're on board with this analogy, I want to ask a few questions. So the first question is, what do you think would happen to the graph on the left, this graph of number of ejected electrons, if the light intensity were doubled or if it were tripled? In other words, if blue light is knocking some electrons off the surface, what would happen if we shined blue light that was twice as bright or 3 times as bright? And the second question is, what would happen to the graph on the right in the same situation? what would happen to the graph on the right if your blue light was doubled or tripled in intensity? So the graphs would look something like this. Again, we're thinking of light as a beam of particles, a bunch of objects that you're throwing at the surface of the metal, such that each one of these objects knocks an electron off the surface. So if you shine brighter light, that means you're throwing more objects at the surface of the metal. And if each one of those objects, each photon, is knocking an electron off, that means that if you double or triple the number of photons, you're going to double or triple the number of electrons that are ejected. But if you think about the kinetic energy of each ejected electron, nothing happens. Each of those photons is carrying the same energy that it was before, so when that energy is transferred to the electrons, they're being knocked off the surface of the metal at the same energy as before. This view of the photoelectric effect is a really radical idea. The idea is that light itself, and not just these abstract energy levels of black bodies, but light itself is quantized. Light itself comes in little packets of energy that are called photons. This is a very important equation related to the energies of photons. This equation tells us that at a specific frequency of light, photons have a specific amount of energy that's proportional to that frequency. E equals h nu. The energy of one photon equals h, which is Planck's constant, times nu, which is the frequency of the light. Again, notice that Planck's constant h is a really, really small number. So the amount of energy in each one of these little packets, each one of these photons, is really small. I also want to show one more equation that's related to the photoelectric effect itself. This equation is basically just a statement of the conservation of energy. It's telling us that if an incoming photon has the energy h nu, that's just the energy of a photon, then some of that energy goes toward removing the electron from the surface of the metal. So the letter on the right side of that equation is a capital phi, a capital Greek letter phi, and it is what's called the work function of a metal. The work function of a metal is basically just analogous to the ionization energy of an atom. It's the amount of energy that it takes to rip an electron off the surface of a metal. So what this equation is telling us is that the incoming photon has energy h nu. Some of that energy goes toward the work function of the metal, physically ripping the electron away from the surface, and all of the energy that's left over goes toward the kinetic energy of the electron. In other words, the energy of making the electron fly away quickly. So this equation really isn't anything surprising, it's just a statement of the conservation of energy. That brings us to the last slide of this video, where we really just want to take stock of where we are. What we've seen is that the reality of light is really strange. In the late 1800s, scientists believed that light just consisted of waves, but what we've seen is that depending on exactly what you're measuring, light sometimes behaves as waves, but it sometimes behaves as a beam of particles. If you're looking at an interference pattern, you're seeing the wave-like nature of light. But if you're looking at the photoelectric effect, you're seeing how light can also behave as particles. These two equations, which are probably the two most important equations in this topic, capture the wave-like nature of light and the particle-like nature of light. C equals lambda nu, speed of light equals wavelength times frequency. That's really telling us the relationship between the wave-like characteristics of light. And E equals h nu, the energy of one photon equals Planck's constant times the frequency, is telling us that the energy of light is actually quantized. It comes in little packets because light is actually behaving as a beam of particles. That's all for now. Next time we'll actually be looking at the fact that matter itself, which we normally think of as consisting of particles, also kind of has this dual nature that leads us to quantum mechanics.